Ionizing radiation emits high energy, and overexposure can cause adverse health effects. It's invisible and can only be detected or monitored by using special detection equipment. Ionizing radiation carries enough energy to free electrons from atoms or molecules. 3 common types you may come across in labs are alpha, beta, and gamma radiation. It's important to understand these types of radiation, as penetration of the skin by ionizing radiation can result in the breakdown of DNA and long-term health issues such as cancer. Alpha radiation. Alpha radiation consists of 2 protons and 2 electrons, and has the strongest ionization ability of the 3, but the weakest penetration. Paper can be used as a barrier against alpha radiation. Alpha rays will not penetrate human skin. However, the ingestion or inhalation of alpha particles presents a serious biohazard. Some common uses are in smoke detectors and pacemakers. Beta radiation. Beta radiation consists of high-energy electrons or positrons and has the median ionization and penetration ability of the 3. Plexiglass or aluminum can be used as a barrier against beta radiation. Beta rays have the ability to penetrate human skin. Some common uses are in medical imaging and leak detection in underground pipes. Gamma radiation. Gamma radiation is considered high-energy electromagnetic radiation, and it has the lowest ionization, but highest penetration of the 3. Lead shielding is the best barrier against gamma radiation. Gamma rays and higher energy radiation has the ability to fully penetrate human skin and tissue, resulting in cellular damage. Some common uses include the sterilization of medical equipment and cancer treatment. It's important to follow the principles of radiation protection. This will help avoid long-term health effects associated with radiation exposure, such as cancer, as well as acute radiation poisoning. Symptoms of acute radiation poisoning include nausea, vomiting, diarrhea, headache, fever, seizures, and tremors. Always ensure you're using appropriate personal protective equipment while using radioactive sources, including gloves. You should also ensure you tape your lab coat sleeves to protect against dangling cuffs and exposure of any skin on your wrist and arms. Follow the time-distance shielding principle. Time. Always minimize the time of exposure. Plan your actions in advance to ensure you spend the minimum amount of time exposed to a radiation source. Distance. Maximize your distance from the source. The further away you are, the less dose of radiation you will receive. Shielding. Always use the most shielding that you can. When using shielding, ensure the appropriate materials are used. For beta emitters, use plexiglass or aluminum. For X-ray and gamma emitters, always use lead shielding. For mixed emitters, use plexiglass or aluminum as your first layer of shielding, closest to the source. Next, use a layer of lead as your secondary layer of shielding. Areas that often require more shielding are stock solution storage and waste collection areas. As a result, make sure you have enough shielding in these locations. You can ensure this by checking with a monitor to ensure the radiation level outside the shielding is at par with background levels. Since ionizing radiation is invisible, it should be monitored using a detector while you work. An exception to this rule is when working with tritium. Because it has such low levels of radiation emission, it will not be detected by most detectors. You can turn the detector audio on and leave the detector near the workspace. Check your gloves occasionally, taking care not to touch the detector surface. Always ensure you're wearing a radiation monitoring badge. These badges will help determine your long-term exposure and dose of radiation. Badges should be stored away from sources of radiation. Ensure you do not store your radiation badge in direct sunlight, as this can register radioactive readings. When monitoring for radiation at your workstation, you can use direct or indirect monitoring methods. Direct monitoring. Direct monitoring can be achieved using a portable radiation detection instrument. Start by verifying that the instrument you have is appropriate for the type of radiation you'll be working with. Remember, you cannot use portable instruments for tritium detection. When you require gamma detection, you must use solid scintillation detectors and not gas-filled detectors. If you're unsure as to which detection device is appropriate, check with your supervisor or a colleague. Once you've determined your detection device, perform some routine checks to ensure it will function properly. Ensure the device has been calibrated within the past 12 months. Check the battery to ensure it's operational. Check high voltage if your device has it. Perform an audio check. Check that the detector window has not been damaged. And finally, remove the detector cover. You can also check the exterior of the device for any obvious damage, such as dents. Place the monitor as close as possible to the surface you're testing without touching it. Move as slowly as you can over the area, stopping whenever you hear or see spikes in the number of events being detected. Always confirm the values at these spikes and write down the measurements in the contamination monitoring sheet. It's important that you perform this monitoring procedure prior to any work with a radioactive source, as these readings will provide a baseline in the event of any spills or accidents. Another method in monitoring radioactive contamination is by completing a wipe test and using the liquid scintillation counter. For this, you will require filter papers, a marker, vials, and scintillation fluid. Ensure that your vials are the appropriate size to fit into the liquid scintillation counter. To start, take a piece of filter paper and wipe an area of about 100 square centimeters, or approximately 4 by 4 inches. Place the paper into the vial and label the vial cap with a sample number. Place a clean piece of filter paper into a separate vial and label this as your negative control. Fill each vial containing the filter paper with scintillation fluid. Place the samples in the liquid scintillation counter. Ensure you make note of which sample is in which spot. You should also ensure you add a sample with known activity. You can ask the radiation safety officer for a standard sample. This will be your positive control. Run the samples using the scintillation counter and analyze your results. Once again, it's important to perform this monitoring prior to starting any work, as these readings will provide a baseline in the event of any spills or accidents. In the event of a radiation spill, the key is to ensure the protection of any persons nearby, then, secondarily, to clean up the spill. Start by ensuring you have the appropriate personal protective equipment, as well as a portable detector that will detect the type of source you have spilled. After each step of the cleanup, ensure you monitor the area as well as your gloves with the detector. Apply the appropriate amount of absorbent material to absorb the spill. Pick up the material while wiping from the outside in towards the center of the spill. If there's any broken glass, ensure you use tongs to pick it up. Use soap and water, or the appropriate solvent, based on what you have spilled, and clean the area of the spill. Repeat these steps as necessary until the detector indicates that you have reached your background level. Keep records of these levels and compare your readings to your initial recordings to ensure you've reached background levels. If you cannot remove all contamination, cover the contaminated area and contact the radiation safety officer for help with fixed contamination. For a tritium spill, you'll have to take wipe samples of the area and check counts in the liquid scintillation counter. Once again, if contamination still exists after multiple cleanings, cover the area and contact the radiation safety officer. Ensure that you use appropriate labels on your waste containers.